Hi all. In this video, we're going to be looking at the graphical solution for the simple minimization problem. We formulated this problem last time. The problem is about a chemical company that's making two types of chemicals, A and B. And they're sold as raw materials to make bath soaps and laundry detergents. And so there were constraints on how many units that need to be produced. You need at least 350 gallons. A minimum of 125 of A, and we had all of these constraints. Based upon that, we had come up with this formulation, right? And the objective here is to minimize the cost. We know that the cost of product A is $2 per gallon, cost of product B is $3 per gallon. So the final solution is to find the minimum of the total cost values with these constraints. Now, these constraints are different from the two other problems that I posted, the furniture problem and the simple maximization problem, because you have a couple of greater than or equal to constraints and a less than or equal to constraint. So let's see what our feasible region ends up looking like, right? So I'm going to start here. So as usual, let's begin by figuring out what our endpoints are, and then we'll take it from there. So the first line is 1 times A is equal to 125. Now this is an interesting line. So in all the other constraints that you've looked at so far, we had both the variables in it, and so we were able to plug in A is equal to 0 and then plug in the other constraint. Let's say the other variable B is equal to 0. But here you have only A is equal to 0 and A is equal to 125, which means that the value of A is always 125. What about the value of B? The value of B can be any number. In fact, what you're saying here is that the value of A always has to be 125 and you don't care about the value of B. So what kind of line is this? So the value of B can be variable, but the value of A is always fixed. So this is a vertical straight line, a perfectly vertical straight line. So when you have, so let's say that we make A the x-axis and B the y-axis, then this is x is equal to a constant. So whenever you have a straight line that is x is equal to constant, that's a vertical line, because the value of x is fixed, but the value of x is fixed, but the value of y can vary on the y-axis. So it's a vertical straight line. So let's draw that. So let's begin. Okay, I had to, the video got cut off for a second. I'm sorry about that. So let me briefly, so we have the A axis here and we have the B axis here, right? So again, so A is 125. So let's say we take 200 here, 400 here, 600 here. So 125 will be somewhere here. So A is equal to 125 will be a vertical line, just like that. This is A is equal to 125. Now we know that the equation, we know that the inequality is A is greater than or equal to 125. So again, so this straight line splits our first quadrant into two regions. You have all the points here and all the points on this side. So which point do we pick? We pick all the numbers on this side because we want all the values of A that are greater than 125. So this is the feasible region right now. So all the points on the right hand side, not all the points on the left hand. So similarly, so if I take 0, 0 and plug it into the equation, I get 0 is less than 125, greater than 125, which is obviously not true. So 0, 0 is not on the correct side of the line. So this is the correct side of the line, right? So that's my first constraint. Let's take the second constraint. So there are no endpoints for this, so I'm not going to do much with it. So the second constraint is A plus B is equal to, the straight line corresponding to the second constraint is A plus B is equal to 350. So this one is easy. If I plug in A is equal to 0, I get B is equal to 350. And if I plug in B is equal to 0, I get A is equal to 350, right? So A is equal to 0, B is 350. A is equal to, when B is equal to 0, A is also equal to 350. So it's 350 comma 350 comma 0 and 0 comma 350. So let's say 200, 400, 600. So 200, so 350 will be somewhere. No, good count. 200, 400. So 350 will be somewhere over there. 0 comma 350. So 350 comma 0 will be somewhere over here. Okay, 350 comma 0. So let's join these 2 points right here. Now this constraint here, I had to keep going back there. This constraint here is A plus B is greater than or equal to 350. So again, if I take 0 comma 0 and plug it in to this constraint here, so I get 0 plus 0 is greater than 350. So 0 is greater than 350, which is obviously not true, which means that 0 comma 0 is not on the correct side of the straight line. So this is the feasible region for this straight line. And so with this straight line, this is our feasible region right here. So it's all of these numbers right here. Right? So let's look at the final constraint. So the final constraint is 2A plus B is less than 630. So let's find the endpoints for that constraint. So you get 2A plus B is less than is equal to plus B is equal to 600. That's the straight line. So if I plug in A is equal to 0, I get B is equal to 600. And if I plug in B is equal to 0, I'm going to get A is equal to 300. Right? Plug in B is equal to 0, 2A is 600, A is 300. So 300 comma 0 and 0 comma 600. Not those points. So 300 comma 0, that'll be somewhere here. And 600, 0 comma 600 is somewhere here. So exactly there according to the point that I marked. Let's join these 2 points. And there you go. So this is the third constraint. 0 comma 6 and 300 comma 0 are the endpoints. But this constraint here is a less than or equal to constraint. So the first 2 constraints were greater than or equal to constraints. Third constraint is a less than or equal to constraint, which means that the feasible region are all the points towards the origin. Because if I take 0 comma 0, plug it in, I get 0 plus 0 is less than 600, which is correct. So this are the feasible points for the third constraint. But we know with the first 2 constraints, these were the feasible points. So our feasible region in this case is right here. That is our feasible region right there. Okay, so it's less than or equal to for the third constraint, and it's greater than or equal to for the first 2 constraints. And so that is our feasible region right there. Okay, right. So the endpoints of the feasible region are right here. So we have this endpoint here, we got this endpoint here, we got this endpoint right here. So the final solution has to be one of these three endpoints. So let's find them. So unlike the previous case, all of these three endpoints, you have to calculate them as points of intersection. So I'm going to call them X, Y, and Z. X, Y, and you got Z. So let's find the 3 points X, Y, and Z. And then the objective function, which was to minimize 2a plus 3b. Okay. So let's do this. So let's begin by inserting another text mark right here. Right, so the first point X is the point of intersection of the vertical line and the second constraint, the 300, 0 and the 0, 600 constraint. So the vertical line and the second constraint and the third constraint, I'm sorry, that right there. So the first, so this is so the two constraints. So we get A is equal to 125 is the first constraint, and the third constraint is 2A plus B is equal to 600. Now this is very easy to solve because the first one just tells you what the value of A is. So if A is equal to 125, I can plug it into the second equation. That tells me 2 times 125, which is 250, plus B is equal to 600, or B is equal to 350. Sorry. So B is equal to 350. So this point is A is 125, B is 350, right? That's my first point of intersection. This down here. Okay. Now similarly, let's find the point of intersection Y. Again, this is also easy because one of the lines is the vertical line. So you have A is 125. That's the first line. And the second line is A plus B is 350. So if I plug in A is equal to 125, so it'll give me 125 plus B is 350, or B is equal to 225, right? Right. So that's 125 comma 225. The other is 125 comma 350. So let's finally find the point of intersection Z. So this is the point of intersection of these two straight lines right here. So that's the point of intersection of the two, the second and the third constraints. So even that is not very difficult to do because the coefficients are actually pretty straightforward. So let's do that. So you get A plus B is equal to 350 is the first line. And you got 2A plus B is equal to 600. So we already have B and B, the coefficients being the same. So I'm just going to take the second, subtract the second equation, multiply it with -1, subtract, how you want to think about it. Multiply the second equation by minus and add the two equations, how you think about it. We're going to do that. This gives us, so A minus 2A will be minus A is equal to B and B get cancelled. 250 minus 600. 250 minus 600 will give us 350. And So this tells us that A is 350. So A is 350, and if A is 350, oh, something's up. I made a mistake. Oh, this is 350. I'm so sorry. A plus B is 350, so that makes more sense. So here this will be 250. So A is 250, and then B is 100. So if I plug in A is 250 in any one of the equation, I get 250 plus B is equal to 350, which means B is equal to 100. So those are my 3 points, right? So 125 comma 350, 125 comma 225, and 250 comma 100. So it's 125 comma for 350 to 125 comma 225, and then the final one is 250 comma 100. Right? Now, just as a point of note, if you see that this solution here and this solution here, they have the same value for A, but this solution has a smaller value for B, this has a larger value for B, and because our objective is to minimize cost, this solution is actually going to be always better than this solution. This is never going to be worse off than this, because this will definitely give you a lower cost because you're making less of B. We are making the same amount of A. So this is never going to be the optimal solution. Technically, these are the only 2 numbers that we need to consider, but because these are the endpoints of the feasible region, I am going to write them out. Right? So 2 times A plus 3 times B. So 2 times A will be 250, 3 times B is 700. So this will be $950. Wait, I messed up. So 2 times A is 250, 3 times B is 1050. I'm sorry. 1050 plus 250 that will be $1,300. I'm sorry about that. So 3 times B is 1050. 1050 and 250 will give you $1,300. Now here it will be 250. 3 times B will be 675. So 675 plus 250 will be 925. Yep. Then 250 comma 100, so it will be 2 times A, that will be 500 plus 300, that's 800. Right. And these are the total cost values, and based upon this, obviously the optimal solution is this value here, because this is the one that minimizes our total cost. So this is the one that gives us the minimum value of cost, because the objective was to minimize the cost here. Okay. And so our optimal solution is to make 250 gallons of compound A, 100 gallons of compound B, and this will cost us $800, which is the cheapest way of producing everything and satisfying all our constraints. So point Z is the best point. Now, like I said, technically speaking, this will never be the solution, because this will always cost more than the solution. So these are our only 2 solutions. And if you look at the solutions, they basically boil down to this. This makes less of A and more of B. This makes more of A and less of B. And which solution we pick ends up with, well, which is costlier. So if A is costlier than B, you'll do one of those things. If B is costlier than A, you'll do the other thing. That's basically what it boils down to, if you look at it, right? So this is a very, very simplified version of a real life problem. So we cannot, all problems will not be that simple. But what I did just there, where I said, well, because this is not a solution, there are only two possible solutions, and we pick one solution over the other based upon the cost. This is called sensitivity analysis. So sensitivity analysis is something that's very important. We will go over sensitivity analysis once we do the Excel solution next week. So once I finish the Excel solution, we'll also talk about this, about sensitivity analysis and why that's important. So sensitivity analysis tells us how sensitive our solution is to the parameters that we assume. So we assumed that we need a minimum of 125. So there's a contract, we need to supply 125. That the production, we need a minimum of 350. This is the processing time. So let's say that a worker is not going to show up for a month. So let's say there's a worker who has to take maternity leave or paternity leave, and they go away, and you are done by a worker, which means that you don't have 600 units of processing time. Then what do you need to do? What is the optimal solution? How many units can you make, and so on? So how sensitive is this final solution to those changes in the parameters? And that's what sensitivity analysis is, and we'll talk about that next week. Right? Okay. So this is a solution to the simple minimization problem. Take care.